Hello, Assalamu alaikum everyone. I am Badrith Tamam and I am here with my team to present our project for data structures and algorithm. This is a peer-to-peer terminal chat with common navigation application. Our team members are Badrith Tamam, Nazia Mahsan, Nishat Roza and Habeba Tasmim Labone. We are submitting these to our course instructor MD Tokir Ahmed, Assistant Professor in Department of Internet of Things and Robotics Engineering at University of Frontier Technology, Bangladesh. Let's get right into the objective of our project. Our goal was to build a chat application that doesn't rely on a central server. It's a peer-to-peer terminal chat app designed specifically for local area networks like university lab or classrooms. The core challenge wasn't just about sending messages, but also about solving key networking problems. Like, how do we find each other without a directory? Or how do we handle multiple concurrent connections? And how do we ensure reliability when a peer disconnects? And we focused on keeping the architecture simple, responsive, and easy to maintain by a terminal interface and a modular design.
Is me, Nazia, continuing to achieve our objective, we set specific technical goals. TSP UDP layer. We use TSP for reliable message delivery and UDP for fast, lightweight peer discovery. Hash-based lookups. We used hash maps to achieve BIGO of 1 performance for looking up peers and routing commands, which is crucial for a responsive chat. Linked list history. We employed linked lists to manage chat history, allowing for BIGO of 1 appearance and efficient memory management. Multi-threading. We implemented a multi-threaded architecture to ensure the UI stays responsive while network tasks run in the background. Laternity UI. We built a clean, structured terminal interface, Jackson percentage. Finally, we use Jackson to save user data and chat history locally. Introduction. Why peer-to-peer online? Now, why build a peer-to-peer app in the first place? Most chat apps like WhatsApp or Discord rely on a central server. This works well on the internet, but in closed environments like a university lab or during a hackathon, a server is single point of failure. A peer-to-peer approach is better because it removes the need for external infrastructure. It allows people to chat directly even when there's no internet access, which is perfect classrooms or local events. Each user's machine acts as both a client and a server, making the system truly decentralized.
Now it's me, Labone. Continuing with slide 4. Problems to solve. Building a decentralized system is not simple. It comes with unique challenges. We had to solve several key problems to make it work. The first was peer discovery. How do we find active users on a dynamic LAN without a central directory? We solved this by using UDP broadcast to find active peers. The second was message routing. When a JSON message arrives over a socket, we need to know if it's a chat message for a channel, a direct message, or a system event. We built a message router to handle this. Third was concurrency. The concurrency was a huge challenge. Our network listeners, heartbeat schedulers, and UI renderer all run on different threads. We had to ensure shared state reminder consistency. The fourth was persistence. Chat history must be saved even after restart. We use JSON files and in memory case. Finally, we had to handle practical issues like username uniqueness on a local network and working around the Windows firewall so peers could connect.
Now it's me, Roja. The slide is about system design architecture. To manage this complexity, we designed the system with a clean modular architecture. On the left, you see the UI layer built with Lantern. It handles rendering and user input but contains no business logic. It forwards action to the core engine. In the center, in our core layer, our chain trained by the P2P engine, this is where the magic happens. The pair manager discovers and tracks pairs. The channel manager manages room and conversation. The message router interrupts incoming data and authentication validates users. Finally, the storage layer handles local JSON persistence using Jackson. The next slide is 6 and this is about networking and pair wire protocols. Let's look closer at how our pair actually communicates. For discovery, we use a simple UDP broadcast of hello Air ID port string. This let us find air quickly without a server. For all reliable communication like chat message, we use TCP with a new line determined JSON format. Our JSON protocol is well defined. A typical message has a type like chat message, heartbeat or presence along with field for the sender, receiver, timestamp and a payload.
It's Tamam again continuing. The performance and reliability of our system depend heavily on our choice of data structures. We use a concurrent hash map for the peer registry. It allows safe concurrent access from multiple threads and gives us big O notation of 1 average time lookups, which is critical for routing messages. For chat history, we use a linked list. This lets us append new messages in again big O notation of 1 and efficiently remove the oldest messages when our 200 message history cap is reached. We use executor service to manage our background threads and Jackson for parsing our JSON protocols.
This is about complexity and correctness highlights. Our data structure choices lead to excellent performance. As we can see in the slide, all our code operation like PR lookups, common displays, and message append are big O1. Even rendering message history of big ON. But since n is kept at 200 messages, it's effectively a small constant. For correctness, our architecture ensures thread safety through concurrent data structure and execute backtask. The hybrid system provides eventual consistency and our bounded history guaranteed deterministic evictions of old messages. Thank you.
It's me, Labone. Continuing with slide 10, UI, commands, and user flow. Let's look at the user experience. The interface uses a three-panel layout you would recognize from clients like IRSSI. On the left is the channel list. The center pane shows the conversation and the right pane lists online pair. The bottom has an input bar and a status bar showing the current user. We support a full suite of slash commands for interaction like slash connect starts a direct message, slash join lets you enter a channel, slash leads show who is online. We also have keyboard shortcuts like arrows or command history and tab for nickname auto completion. The login flow is straightforward and we provide audio feedback for incoming message.
It's me, Tamam again, discussing advantages, limitations, and future work of our project. Our app has several clear advantages. It's cost efficient because it has no central server. It's reliable for online LAN use and it has persistent local history and it's responsive thanks to its multi-threaded architecture. However, we also acknowledge limitations. Discovery is LAN only, messages are transmitted in plain text, and we don't have delivery acknowledgements yet. Also, JSON storage is practical but not as robust as real database. For future work, we would like to add end-to-end encryption, support for STUN or relay servers for internet connectivity, and replace JSON storage with SQLite for better performance and integrity.
Conclusion. In conclusion, our project successfully demonstrates a fully functional peer-to-peer chat system that addresses the core challenges of distributed communication on a LAN. We have applied the data structures and algorithms we learned in this course, like hash maps, linked lists, and concurrency, to solve real-world networking problems. We have delivered a self-contained distributable Windows application that allows users to chat directly without a server, providing a secure and responsive experience in isolated network environment.
Here are the references we took for our projects.
Thank you for your time. We are happy to answer any questions.